Hello! It's Wednesday evening, 7:30 p.m. AWST, and that means must be time for another Astronomy Wednesday talk. Hello, I'm Greg, and welcome to the ICRAR Astro 3D session. Now, ICRAR stands for the International Centre for Radio Astronomy Research, a very important organization, part of Curtin University and the University of Western Australia, discovering the hidden universe through radio astronomy. And of course, Astro 3D, the ARC Centre of Excellence in all sky astrophysics across many organizations around Australia. But first things first, I'd like to acknowledge the traditional custodians of the land on which we're speaking, the Whadjuk Noongar land, and pay our respects to elders past, present, and emerging. Now, today, it's not just, as per usual, it's not just me rabbiting on. We have experts come to give their amazing information about what's going on. And so I'm going to throw it now to Dr. Brent Groves. Hello, Dr. Brent. How are you?
G'day, Greg. G'day, everyone. Here to share the joy in some of the things I work on in astronomy at ICRAR.
Brilliant. So, Dr. Brent, can you just give a potted history, a 1 minute précis on who you are and why you're chatting to us today?
So, as you can tell, I'm an astrophysicist coming from Australia, but, I started here, went all the way around the world studying various things and ended back in WA. So the various things I study tend to be galaxies like our Milky Way. That is, how they move, how they grow, how they shrink, and how they, die over time.
Do galaxies have a habit of dying over time a lot? You have to watch out for that?
What they do is they tend to just stop growing, get big, hit middle age, expand a bit on the bellies, and eventually sort of just become what we call red and dead, where they just sort of just flop there. So so galaxies they grow, they merge like marriage, they eventually become big and round, and eventually what we would say is that just sort of end up being sedate in their old age.
Sounds amazing. Let's hope how my life ends up. It just sounds the best. Lucky galaxies. But before we're going to talk about galaxies tonight, though, we're going to be talking about something else. Your topic is about how things move in the sky or seem to move in the sky. But even before that, we have to get to, is it science or is it art? So we've put up a picture on all our socials. We like to point out have these amazing pictures. Here it is for all our listeners and watchers, not just listening, but people watching as well with the vision. How exciting. And I'm just looking at dots now, lots of dots, lots of lines and dots. Dr. Brent, do you have any idea what this might be?
I actually have no idea. Now, I think there's definitely lots of information here. I can see that dots all have different colors, different sizes, and different positions. And so that must mean something. So they've got different positions in what I would call three-dimensional space. They must mean something about, be it stars or galaxies, which is interesting. Now, the different colors which tell us something as well, and then the different sizes must tell us something as well.
It's pretty crazy. It's really, it's a mad one. So we're not going to give it away right now. In fact, I have no idea what it is, and you don't know what it is. We're going to tell people on at ICRAR, so at ICRAR on Twitter on Friday. We'll find out what it is then. So if you have some guesses, go to Twitter, put your guesses in. There are no prizes except knowing what cool things are. So, but you can still put your guesses in.
Knowing that you got it right, I think is
the ultimate prize. Bragging rights. All right. I think now it is time to get into some serious science about the heavens in motion. Take it away, Dr. Brent.
So I thought I'd give a picture on a little bit of what I work on, but in general, what we do in astronomy in trying to work out what's happening out there. And specifically, I thought I'd start off with one of those interesting things that the heavens in motion. That is, things are moving in space, but it's very hard sometimes to work out how they're moving. And I thought I'd sort of take you through a story about the movement of the universe, starting from small to big. So the thing is, stars look constant out there. We look out there every night, we see the same stars, and that's great. But in reality, everything is moving. We're moving on Earth. The sun is moving around the Milky Way. The Milky Way is moving. And so it makes things very different. So given enough time, the universe would look totally different. And it's just a question of what enough time is, because it depends on how fast they're moving. Okay, and that's one of those interesting things, is that in space, objects move amazingly fast. What we talk about when we talk about things moving in space are kilometers per second, not kilometers per hour, but kilometers per second. They're moving 1,000 times more than that. So we take something nearby to us, right? So the space station, the International Space Station, is actually moving at about 7.5 kilometers per second. So we can see it move around in orbit around the Earth. We take the Earth, when it's going around the sun, it's moving 30 kilometers per second. Now we take the sun itself, if we consider how it's moving around the center of the Milky Way, and it is moving around the center of the Milky Way, it's moving 200 kilometers per second. Yeah, think about that. We can talk about, the fastest runners in the world are moving sort of 10 meters per second. All of this is moving thousands of times faster than that. So things move fast in space. Now, of course, when we talk about movement, the first thing that's obvious when we look up at the sky is, of course, the Earth movement, or rather, we can see the sky move overhead as the Earth rotates. And if you go to a very dark place out there, and what you see here is a wonderful photo of the night sky above one of the largest telescopes in Australia, the Anglo-Australian Telescope, which is in the middle of New South Wales at Siding Spring Observatory. And if we stand out there, over time, we get to see the sky slowly move overhead as the telescope itself is looking at objects in the night sky. And in fact, at this point in time, I'm right inside that telescope when these pictures were taken. So looking at various things in galaxies there. And so one other thing I'd like you to see as there is that at the start of this image, you'll see this quick flick of light. And that's another thing that we see moving out there, right? And that's satellites. So shooting stars and satellites are things that we can actually see moving by eye. That is, we go out there, like hopefully some of you did last night, at least those of you who weren't clouded out, and you can see meteorites and shooting stars fly across the heaven. And so you can easily see these because the stars look constant, but the shooting stars move quite rapidly. Now, if you keep looking up there long enough, eventually you'll also see other objects moving. And these, apart from the planes, are satellites moving around us. Especially at dawn and dusk, you can see the reflection of some of these satellites that go around. And if you look long enough and know when you're looking, you can even see the International Space Station move around us. And so that's what you see here. Somebody's taken a long exposure of the night sky, and that track you see, while the stars are constant, is the International Space Station moving across the night sky. And so you can actually see this by the naked eye, right? You don't need binoculars, you don't need a telescope. All you need to do is just look up where is the International Space Station at any time, and depending on where you are on Earth, you can see it pass overhead. And you can even see it pass overhead here in Perth, over the East Coast in Australia. I've seen it in Canberra, I've seen it here. And so what I do is use these apps. So Orbitrack for Apple, the ISS detector for Android, and many other Sky at Night apps will tell you exactly where the International Space Station is right now. And you can even plan ahead when to look out there to see this beautiful object track overhead. And people with telescopes can even get start to see the International Space Station, right? Instead of just seeing this line moving overhead, you get to actually see sort of the structure and the solar panels of the International Space Station. Just the other day, I saw this wonderful image online taken by a telescope of the International Space Station moving. So that's great, except for astronomers like myself, satellites can sometimes be a pain. Right? And so what you see here is a wonderful real data from a 10-minute exposure from a big telescope in the US. Right? And so what you see here are bright stars, galaxies, and you also see a lot of mess there. And some of that mess is what we would call cosmic rays, That is things flying through the heaven and hitting our digital camera, and that leaves a mark. And then, of course, the most obvious thing there is this long track that goes straight across the image. And what you're seeing there is a satellite that happens to go across the part of the sky we're looking at with that telescope over time. And now, if that was truly what we always had, then you would see this in all of the beautiful images like you see hopefully online, and I'll hopefully show some tonight. Is what we do is we actually remove these, and we do this by keep taking exposures one after the other. And all of these things, the stars, the galaxies, are all constant, but the satellites are not in every image. Those cosmic rays are not in every image. And we work with this data to remove all that and end up with a beautiful image at the end. Now, let's move on to something bigger that we can see move in the night sky. And these are the planets. Now, if you stand out there one night, you won't see the planet move, right? But you stand out there night after night, or every night on the same day in a month, you will see the planets move relative to the other stars. And this is how we know the planets are special. Way back when the early people were looking up at the night sky, they could see all these wonderful twinkling things, and then these brighter things that did not twinkle in the night sky, and that happened to move across the night sky as the Earth, as the days went on. And so these became our planets, or gods in the old days and planets now. And so by taking an image of the same spot in the night sky, night after night, people can make the tracks of how the planets move across this. And so what we're seeing is an interesting combination, right? So the planets are all moving around the sun. But the thing is, the Earth is one of those planets moving around the sun. And so it's the combination of the Earth's movement and the other planets' movement that leads to these wonderful tracks. So if we look at Saturn, that's that, like bright dots on the top left there, you can see that it just makes some sort of circle. And what's happening there is mostly just the Earth moving, because Saturn moves quite slowly around the sun because it's quite far out. Now, Mars, which is the bright red dots that move across the screen, orbits quite quickly, just like Earth, but slightly slower than Earth. That is, its year on Mars is longer than a year on Earth. And so what happens is that Mars tracks across the night sky, but then because Earth's moving, it tracks backwards. And this is what we call a planet being retrograde. It took me a long time to work out what retrograde motion is, but it's really just the position of those planets and Earth and how they change over time that causes that movement. So we can actually see planet move with our own eyes. We just go out night after night and we'll see, oh, look, it's in a different position. And that leads to that wonderful tracks you can see here. So let's move on to something even further away, stars. And so we can actually see stars move across the night sky. So stars that are very close to us and that are moving faster than other stars can actually be observed to move. Now, instead of talking in a single night or, days across a year, we really have to talk about multiple years. And so what you see here is an image of Barnard star in 1985. Now, going back 5 years later, the star has moved. So we keep observing it every 5 years, and you can see that relative to those other stars, Barnard star is moving across the night sky. And that tells us that that star is both close and moving quite fast. Now, we can even see stars that are further away move like this. But to do this, we need much bigger telescopes, and they need to be moving much faster. The best example of this is actually the center of our own Milky Way. Right at the center, when we look up at the night sky, you can see those bright stars, you can see the great emu, that big dark patch across the sky. Right at that center of that dark patch is the center of our own Milky Way. And if we use the best telescopes to look right at that center, we can see stars there. Now, interestingly, if we look at long enough, and that is over years, we can see those stars move. Now, what makes the movement of those stars so interesting is that not only are they moving fast, they're moving in very weird motions around something that we can't see. Right? And interestingly, there's something that we can't see is huge. It's hundreds of thousands times the size of our sun, all in a tiny little amount of space, and we can't see it. So this has to be a black hole, right? And it's one of the best evidence we have, apart from those recent images of a black hole. We can see something that's heavy, hugely heavy, in a tiny amount of space that's not visible. And so this is the supermassive black hole right at the center of our galaxy. So moving right around those. And let me just go backwards and move that again. So just watch those stars go round and round, and you can see they go flick as they go very close to that black hole and move around. And that bright one that they label is actually orbiting the black hole, just like the Earth orbits the sun. Okay, so that's, to me, is an amazing, discovery and showing what we can do with the movement of the heavens. Now, going back, when we talk about the movement of the stars, there's one thing we have to be careful of, and that is, of course, that the Earth is moving around the sun. And so when we look at the stars out there, the Milky Way, in December, and when we look at the stars in June, we might see some of those stars move. Now, the problem is, it's not those stars that are moving, it's the Earth that's moving, and that's causing the star to move. So if we observe that same star in December again, it'll be back to its original position. That is, the star will do a wobble back and forth because the Earth is moving. And this is exactly like when you're driving a car. When you're looking at things nearby, the side of the road, trees next to you, you can see those zoom past. But if you look far away in the distance, the Perth Hills, the mountains, the Blue Mountains, you will see those stay fairly constant or move very slowly. Right? And that's all about that they're much further away than those trees near us. Now, for us astronomers, this is a great idea because we know how the Earth moves around the sun. We know how far away the Earth is from the sun. So we can actually use the movement of these stars to tell exactly how far away that star is. And this is great because determining distances to objects in space is hard. Right? We can't get a ruler and tape measure and measure it out to it. Right? We don't know how bright it is, so we can't tell how far away it is. And so we have to use very specific things to tell us how far away that object is. We either need to use exactly this, what we call parallax, to measure the distance to stars. And then for certain stars, we do know how bright away it is. And so if it's further away, it'll appear fainter. And then we use other objects and other tests. And this is what we call a distance ladder. And so we use each of these steps to tell how far away each part is. And for this is how we work out how big the universe is. It's only thanks to the Earth moving around the sun that we know how big the universe is. Yeah? So it's all little connections in these kind of things. So movement is hugely important to determine sizes as well. Now, I've talked all about being able to see things move. Now, this is great, but for things that are much further away, we won't be able to see them move, right? So even if they're moving thousands of kilometers per second, they're so far away, it would take thousands of years to actually see this thing move because space is so big. And so what we have to do is use other ways of measuring how fast things are moving. Now, the best and most useful example for this is what we call the Doppler effect. That is, now we know this, and you've all know what the Doppler effect is, or at least aware of it. all right, because we use this, we hear this, for example, when a siren is coming towards us, it becomes higher in pitch, and as it moves away from us, it becomes lower in pitch, right? So think about it, it goes, wee, 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 right? And that's the Doppler effect. We use the same Doppler effect with ultrasound, right? So we use this to tell both how far away things are and how things are moving, right? So the Doppler effect is used exactly to measure baby heartbeats with an ultrasound. And in fact, I know this well because we just did this the other day with my partner and saw that heartbeat move blue and red as the heart pumps blood around the baby's body, right? And so that's the Doppler effect. Now we even can do this with light, right? So we've heard about Doppler effect with sound, we've heard about this with ultrasound, but we can actually use this effect with light. Now I'll take a little bit sideways to sort of show how we do this. So let's take the sun. We all know that if you take a little prism or raindrops, it'll split that light into a rainbow. Now, if we do this big enough, what we end up with is what's called the spectrum of the sun. And that's exactly what you're seeing here is a solar spectrum. You see the beautiful rainbow we're all used to from blue to red, but if we look in detail, we see a whole lot more there. We see all of these dark patches, which is interesting because we would expect the light to be everywhere. But what those dark patches are really telling us is about elements like hydrogen, carbon, nitrogen, all of those things that are in the atmosphere of the sun. And this is great because many people use all of these little lines to measure how many elements are in the sun. And we can even do this around other stars. So people use this to say, well, the sun has this much carbon relative to hydrogen, and this star has less carbon relative to hydrogen. So does that mean it's metal poor, or does it mean it formed earlier, and all of this? And so these little lines you see here are hugely important to work out how many elements are there in the sun, how old is that star, and how is that star moving? And that's the part I'll sort of talk about now. So what we do is we take those wonderful little lines and we look at them. And we see, like I said, hydrogen, sodium, and magnesium. And we can see the sun and we can trace all of those. Then we take a star and we look and we see very similar lines, but they happen to be in a different position. Right? And that's telling us something, because that's telling us about how that star is moving, because the Doppler effect on light is doing exactly the same thing to those lines and the color of the star as it is doing it to the sun. And so by looking at those lines and saying, well, I know what the laboratory has and I know what the sun has, and so I know where those lines should be, but because light has shifted, just like sound has shifted as things move towards us and away from us, we can actually tell how fast this object is moving and whether it's moving towards us and away from us. So look at those two objects I've got there. The sun is exactly the same between those two pictures, but those two stars are very different. Right? And look at those and you'll see that you can work out whether that's moving away from us or towards us and whether it's moving fast or slow. So have a look and I'll show you the answers. There you go. So the top one is what we would call is red shifted. That is, those lines are shifted towards the red, and that means the star is moving away fast. Now the gap between those lines, so if you look at the sodium of the sun and the sodium of that star is quite big. It means that star is moving away fast. Now the bottom one is a blue shift. That is, those lines are shifted towards the blue. And that gap is a lot small. So that star is moving towards us very slowly. And so we look at this and we look at many stars, and we can tell how the space around us is moving. And from this, we can tell how the sun and those other stars are orbiting around the center of the Milky Way. And so again, this is how we determine movement for a lot of objects out there. So stars, galaxies, and other things. But if we look in close detail, so I take that magnesium line and I look in very much detail at that star. if I look long enough, I might start to see that magnesium line wobble slowly backwards and forwards. And that tells us something. And that tells us that there's a planet around it. So we know that the Earth orbits the sun. But do you know that actually the sun is doing its own little orbit too, right? The sun is pulling the Earth, and that's why the Earth is going around the sun. But the Earth is also pulling the sun. And so over time, as the sun pulls, as the Earth goes around the sun, it's being slowly pulled backwards and forwards. And so we can see that wobble. Now, obviously, if you've got a bigger planet, you'll have more of a wobble because that bigger planet, like Jupiter, will pull that star more. And likewise, if that big planet Jupiter is closer to the star, like Mercury, it moves around much faster. And so it wobbles more quickly. And so this radial velocity method, is what we call it, is one of the best ways we have of actually finding planets out there. And so what we do is we look at every single one of these stars, we look at those lines, and we look at those lines over time. If they're constant, they're either small planets or planets that are far out or no planets. But given enough time and a big enough planet, we can watch this wobble. And so from this, we've discovered a huge number of planets. I forget what the total number is. It's like 1,500, I think we're up to now. It's like a huge number of planets. And over time, we're discovering more and more by just observing the same stars for longer and longer. And given enough time, we might discover planets like the Earth. And so you've heard about this, near-Earth objects. And that's just because we've been observing these stars for years at a time. Right? So to find something like the Earth, it'll take 1 year for that wobble to occur. But of course, you see the wobble once, you're not sure. So you need to observe it again and again and again. And that means we need to observe the same star year after year after year to see that same wobble year after year after year, tell that there is an Earth-sized planet in an Earth-sized orbit around that object. So moving forward, we can also see gas in exactly the same way. So when there's hot gas that's been heated to a plasma, it emits lines, just like those absorption lines we see on the sun. And so we can match these up. And so what I show here is the hydrogen absorption spectrum, hydrogen emission spectrum. And these lines will be shifted exactly the same way as the stars. So we'll see them shift backwards and forwards depending on the gases moving towards us or away from us. And so we use this to determine how galaxies are moving. Right? So we're seeing the stars and galaxies in a galaxy move in exactly the same way as we're seeing the stars move in our own Milky Way. So what I show here is a wonderful galaxy. Now, it's not so wonderful it has its own little name. We just call it NGC 1566. Right? And this is an image taken with by myself and others. Right? So you're seeing now here real data where we've taken this. Now, what's special about this data is that it's 3D. Just like the Astro 3D, it's 3D. So we have light across that wonderful spectrum. So we have that red images, we have the blue images, we have the green images, we have the orange images, and it's split up so finely we can see even those lines. And so what that means is when we look at it, we can see the gas move around this galaxy. And so what you see here is gas moving towards us, that's the blue, and gas moving away from us, that's the red. And so what's happening is the galaxy is rotating just like this. You wouldn't think it by looking at it, but actually very slowly, that galaxy is moving like this, right? It might also be moving like this, but we can't see that because there's no towards and away from us motion. It's moving side to side. But we know at least some part of it is moving towards us and some part of it is moving away from us. Now, when we look at the stars, we see exactly the same thing. That is, the stars are moving away from us and towards us, exactly the same pattern. But there are slight differences that tell us that sometimes the gas is a little bit dragging or sometimes the gas is a little bit leading. And from this, we can start to work out how gas is moving in galaxies and how that gas might end up collapsing to form the new stars that, like our own sun, and those new planets. And so that's work that I actually do here. So you're seeing here images hot off the press, or hot off the telescopes, as it were. Right, so let's move on. Now, we can take this and doing galaxy against galaxy. We can see how different galaxies move. Right? And now this is really interesting. When we look at galaxies and measure how far away they are, using those distance ladder I told you about, we see that galaxy after galaxy, as it's further away, is moving faster and faster and faster. This was discovered back in 1929 by a guy named Edwin Hubble, the person the Hubble Space Telescope is named after. And this is an important discovery. He realized, using this, that the universe is actually expanding. Right? So take that and think about this. So things that are close are moving slowly. Things that are far are moving much faster. Okay, and hopefully you've heard about the bubble analogy. And so what I show here is a video showing exactly that idea, that as the universe expands, things move further away. And as you're further away, you move faster and faster, because it's like a bubble expanding. Now, this is really interesting because it means the universe is growing over time. And this is how we came up with the idea of the Big Bang. That is, if you take the universe as currently expanding, it must have been much smaller back a long time ago. In this case, 13 billion years ago. All right? And it keeps on expanding. And this leads us to sort of that final point, is that we're doing this again and again and again on measuring more and more galaxies. And this led to the Nobel Prize winner, Brian Schmidt, realizing that by looking at galaxies further and further away, not only are they moving faster, they're accelerating. Right? That is, the universe is not only growing, it's growing faster and faster over time. And so this has led to the wonderful theories of dark energy that we hear and know nothing about, and led to the Nobel Prize for Brian Schmidt. So thanks to all of these little steps that I told you, we now know that the universe is expanding, and not only expanding, but accelerating. So we'll never have what they call the big nab again. In other words, the universe will never collapse. It'll just get bigger and bigger and bigger and bigger over time. So everything in space is moving. The Earth rotates, the sun orbits, the Milky Way rotates and moves away from other galaxies. Speeds in space are fast, and the universe is accelerating. So thank you, and hopefully you've all got lots of questions.
Thank you very much, Dr. Brent. That was really interesting. It always blows my mind how much the universe is all moving, because it always feels very still, hopefully, unless you've been drinking. But really everything's whizzing around.
Here's at that stage.
We're not at that stage of isolation at this point. So I have a question, and it always comes down, you talked about the universe expanding, all the galaxies sort of moving away from us, the universe expanding. And the question I'm always asked is, what's it expanding into?
It's a very good question. And it's hard to imagine, because there's not this space in which the universe is expanding into, right? It's the whole idea is that the universe is not expanding into anything, although there are some weird theories that do have something like this, which is called string theory. But really, and the idea is that just everything is moving further away. So space is itself expanding. And that's a very weird thing to have, because we can picture the balloon, but the idea that space is expanding and there's nothing to expanding to is just something that's very hard to get your mind around. And so, I very much understand this question, but the idea is that there is no expanding into anything as part of this, right? So, sorry, there is nothing expanding into, but it's just growing over time.
Growing over time. And it's going to go faster and faster and faster. So what does that mean then for us? Does that mean that one day we're going to be all alone in the universe?
It does mean. So, we have our near neighbors, like the wonderful Magellanic Clouds we can see here in the southern hemisphere, and then the Andromeda Galaxy, which we can see in the northern hemisphere. Now, these things are close enough to us that they're just going to stay, together like neighbors. And in fact, eventually they'll just all collapse into one big galaxy itself. But galaxies that are further away, they'll just move further and further and further away. So eventually, and when I say eventually, I'm talking billions and billions of years in the future, space will be very, very dark. Apart from our own stars, we won't see any other galaxy out there, because things just will move so far away, it just becomes, one giant background. So yes, it's a very sad future for us, but I can tell you that that future is a long, 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 long way away, right? So you don't have to worry about that. I think the sun will end in terms of a big explosion before then, and that's another story to tell you.
So what's the most exciting thing you've discovered in your research? What's like the one thing that you discovered or that you worked on that you're like, my goodness, that's something we just didn't know yesterday that really excited you?
So so this is where, I wanted to show something that, like these images here, as I said, are hot off the press. And so by looking at this, the way the gas is moving, we start to see how it falls into those wonderful spiral patterns that you see here in that color image. Right? And those spiral patterns you see there are signs of where stars are newly forming. So what we're trying to find out, and that's what these images are now starting to show us, is how gas moves in galaxy. It doesn't just rotate, it slowly moves and collects around these spiral arms and collapses to become dense enough to form the next generation of stars. And so we're doing this now, currently, with these images I'm showing you here, to work out how fast gas moves and how quickly it is then blown away by those stars that are now newly forming. So so that's new, hot off the press sort of discovery for you.
Now, the image on the right, is that taken with a radio telescope?
No, the image, both the image on the left and the image on the right are taken with the same telescope. So this is a big, giant 8-meter telescope. That is a mirror that's 8 meters in diameter on top of the mountains in Chile, where it's very, very clear above all of those clouds and the sky is not moving that much, but it's taken with the same instrument. So the left and the right are all from the same data. And that's that Astro 3D that you hear about, right? That 3D image is able to do multiple things. It's able to tell us where the stars are forming. It's able to create beautiful images like you see here on the left. It's able to tell us how the gas is moving. It's able to tell stars are moving. It's able to tell us how old the stars are, all in the same image. Now, that's a lot of information, and so it takes us a lot of time to extract it all, and it takes us a lot of time to discover it. Right? So if we look at that image on the left, if we zoom in enough, we're seeing images and regions that are size of our star. Right? Or we're seeing individual stars. Okay, stars that are slightly bigger, so 10 times bigger than our sun, but we can see that with those images.
That's very exciting. So those new gas, there's like in the right-hand image, like the blue areas, blocks of gas and that sort of stuff. They're going to collapse down into multiple stars, kind of like Orion's Nebula, like stellar nurseries.
Exactly like Orion's Nebula, right? Except these collapse of gas is much, much bigger than Orion's Nebula. When you look at Orion's Nebula and take it and put it in this galaxy you see here, it would be puny. But if you can look, and you'll see these little bright red dots across that image, those are regions where stars are forming at sort of, one sun per year, right? Can you imagine that? So that's one sun forming every year in that tiny little space. Okay, now that tiny little space is quite large compared to the sun, but still, that's a huge amount of suns forming all in with that tiny little area.
Amazing. How long did it take you to collect the data to make this plot?
So this, because it's a big 8-meter class telescope, it doesn't take as long as if you had your own small telescope there. So it's so big on the sky, which means it's tiny and hard to see by the naked eye. It's taken us about, like at least one night on that big telescope to take just this image. But the telescope is so good, we can do this all in one night. Now, the telescope is also so good that everybody else wants to use it, and that's why it's so hard. So people want to use it to find planets. People want to use it to measure how how many elements and how much uranium is in this star over here, right? And so everybody wants to use this to make these amazing discoveries. But so one night is a huge amount of time for all this. So overall, we have 20 galaxies, and this has taken us 100 hours, which means it's taken us about, a couple of months on telescope time to actually do this.
Amazing. That's really, that's exciting. I just wanted to say thanks to Bo, one of our listeners, who said, say thanks, Brent, very interesting. And I absolutely agree. And I think, unless there's any more questions from the audience, we have to let Dr. Brent get back to discovery. Oh, actually, I have one last question. Seeing you're doing all this work on NGC 1566, are you allowed to call it Brent's Galaxy?
Unfortunately, no. Other people have discovered this galaxy long before I did. The people have discovered and named their own galaxies, but they're much further away. So we're talking, thousands and thousands of times away. And people have done this, and they've named them after, for example, big soccer stars like Cristiano Ronaldo. I won't say who named that one, but people have done this for these more distant galaxies because there's a lot more galaxies out there. So, we end up just naming them boring numbers just so we know exactly where it is.
In the future. Thank you very much, Dr. Brent Groves, for pointing out how things